Dear friends, welcome to the eighth lecture of our differential geometry course in the 2020 Corona semester. Today we will start section 5.5 and I hope to finish this today. Let's see, the implicit case. So this time we will assume that our surface is defined via function. That's why we call it the implicit case. So let M be a surface in R3, surface, given by like this, the zero set of a function for some smooth function g from R3 into R. All right. We assume that 0 is a regular value for f, for not f, sorry, for g, and thus the derivative map g star or dg from the tangent space to R3 at the point P to 0, the tangent space of real line at 0, which is 0, for any P in M. Well, note that since M is defined by G equals 0, we know that P is in M if and only if GP is equal to 0. Okay, that's why this tangent space is mapped here, and this the regular value means that the derivative map is onto for NP is surjective. Well, this is surjective means how this map is defined. G star is defined like this. G star, if I take matrix representation of this in the standard basis for R3 and R, then we know that this is given by the gradient matrix. Okay, so UI, where we have this actually, G star at any vector, let's say, at any vector V is just gradient of G at P dot product V. So it is just I from 1 to 3 del G del Xi at P times Vi, where V is the vector, let's say V1, V2, V3, or maybe I should write it like this. Okay, well, this map is onto means then the gradient is never 0, right? So this shouldn't be 0. Hence, you see that this gradient is not 0 for all P in M. Okay, well, take any path on the surface. So let's say this is our surface, and let's take a path alpha. Let alpha uh, sorry be in a path, any curve. Then of course the tangent vector to alpha is always in the tangent space. Uh, then I have this g of alpha t is, of course, this is on the surface M, therefore this is 0 for all t. And we know that g, sorry, alpha prime t is a vector at the point alpha t to M. Now let's take derivative of this equation. I have 0 d dt of g of alpha t. Well, this is just, I apply Leibniz rule. So this is just the derivative of g at alpha t, dot product with alpha prime t. So maybe I should write like this. So the gradient at alpha t, dot product, the derivative of inside, which is this. So for all t. This means what? This means uh, these two vectors are always perpendicular, and I know that alpha is an arbitrary vector in the tangent space, right? For each direction I can choose such an alpha. Therefore we see that, and this is perpendicular to all the tangent vectors in alpha in the tangent space. Therefore this is perpendicular to the surface. Okay, so our so the conclusion is that our gradient vector is always a normal vector to the surface. So gradient vector is something like this. Let's say. Okay, so this is always perpendicular. Therefore, if we want to choose a normal vector to the surface, we may choose the gradient of g. Okay. So let z be the gradient field, and then u, which is z divided by its length, uh, be be the uh, be the unit normal vector field on M determined by uh, Z. Okay. Well, uh, let S be the shape operator of M corresponding to this, to the normal field U, which is Z over norm Z. Then we know that then by the definition uh, the shape operator at any vector is just the derivative of the normal field along the vector v for any v in TPM. We know this. Now let's write let's write z, the vector field z in coordinates, which is the gradient vector in coordinates. So this is what? Let's say zi ui. Then the covariant derivative of z in the direction v is what? We know that this is just I from 1 to 3 v of zi and then ui, and the covariant derivative of u in v will be what? This is the covariant derivative. U is just z divided by norm of z. So this is the vector field z multiplied with a function. And whenever we have a vector field multiplied with a function, then its covariant derivative obeys Leibniz rule. So this is just covariant derivative of z divided by, times the function plus the covariant derivative of the function times the vector field. Of course, you know, so this is just 1 over z covariant derivative plus, what is this? Covariant derivative of a function is just the partial derivative of directional derivative of this function along the vector v. So this is just v of this times z. This is a scalar times the function z. Okay. The observation is the following at this point. This vector field, note that, so let me write here, this part is, because z is in the normal direction, is normal to the surface. And we denote it by minus nv, the normal direction corresponding to this field, the normal part of this field. So our shape operator becomes this, which is by definition this. So this is the covariant derivative of z divided by norm of z times nv. Okay. We have some observations. Let's see these. First one is this. If W is a vector in the tangent space, then NW is normal to M and thus parallel to NV, because both NV and NW, right? I know that NV is So this is our surface, let's say, at any point. NV is normal vector and NW is normal vector. But these are normal to the tangent space, which is two-dimensional. Therefore, these two vectors must be parallel. Okay, but the obvious conclusion is that then in this case, the cross product will be zero. Okay, this will be important in our computations. We will see in a minute. Also, if y is any tangent field, tangent vector field to M, then of course y cross and v is perpendicular to both well, it is both perpendicular to y and nv, but what we care is about its being perpendicular to nv. But this is the normal vector, and this is perpendicular to this one. Therefore, this is another tangent field. Then is perpendicular to nv, and thus y cross nv is another tangent vector field. Okay. So using this observation, we will state and prove the following lemma. Let Z be a non-vanishing, well, I should say not non-vanishing, nowhere zero normal field on the surface M if V and W are tangent vector fields on M such that their cross product, since they are both tangent, their cross product is parallel to Z. But let's assume that this cross product is so V and W are chosen so that this cross product is Z. Then we have the following conclusion. The Gaussian curvature is equal to the following expression. So this is Z dot product, the covariant derivative of Z, cross the covariant derivative of Z. Again, the first one is with respect to the field V, the other one is with respect to the field W, divided by the quantity, which is the fourth power of the norm of Z, and we assume we have also this conclusion, I mean this formula for the scalar curvature. The scalar curvature is minus Z dot product with the covariant derivative of Z with respect to V cross product with omega plus W, sorry, and then we have the dual term, and here we have third power. Okay, let's see why this is true. Proof is actually similar to the ideas we have seen already. Let me uh, write them down. You know, from section 5.3, or maybe I should say from the book, I mean, lemma 3.4, that Gaussian, sorry, shape operator uh, evaluated on V and W, the cross product is of these two vectors is just the Gaussian curvature times the cross product of V and W. And the second is, recall we have proved this equalities, and we actually uh, made use of them in some computations. And then from the above computations, we have what? The shape operator on V is just minus the covariant derivative of z with respect to V divided by this plus the normal part. And similarly, of course, this is just the same thing, the covariant derivative plus the normal part. All right. And then we do the following. Uh, by assumption, by the assumption, V cross W is equal to Z. Now take, so this vector here is just Z. Take the dot product, taking dot product, inner product of the equation 1 by Z, which is V cross W, we get what? We get this. So here I will have a dot product of Z with Z, so it will be norm of Z square, and then I will divide uh, this equation by the norm of Z square, and we will get the following. Let me just write down. We will get Kp, which is just dot product of this with Z, sorry, divided by norm Z squared, or let me just write, okay, norm Z squared, which is Z with dot product Z. And then we do what? Well, let's see what this quantity is. SV cross SW. I have the expressions for SV and SW. Now, SV cross SW has 4 terms. Let me write down the terms, 4 terms. First of all, we have this divided by norm Z squared minus norm Z minus NV cross norm Z, and then I have NV cross NW. But we already know that the last term is 0, and this term is we know that perpendicular to uh, normal vector. So this is normal to z, and similarly this is normal to z. Therefore, dot product of these two with z, with this quantity, will give me 0. So the only surviving term will be this quantity times z. So let's see. Uh, Hence, we see that the only surviving term is just, so Kp is just z dot product with this quantity, and here I have z squared, but already here I had another norm z squared, so it will be norm z to the power 4. So let me just write this down. Okay, so this finishes the proof of the first part. For the second part, which is about the scalar curvature, uh, the okay, uh, okay, uh, similar arguments, yani aynı şeyler, arguments prove the second statement. Okay. So this finishes the proof of the theorem. Uh, Here we have some examples. Actually, we have one example. Let me. Okay, so let M be the surface defined by this equation. Uh, Equals 1. I could have written this as minus 1 equals 0, but this would be more convenient. What is this? This is an ellipsoid, right? An ellipsoid. Okay, now what is z? Z, then the normal field z, which is the gradient of g, but we will take not g gradient of g, but half of it is given. What is z? So I will take gradient of this and divide by 2. So when you take the derivative, you will get 2x1s and so on. So I divide by 2, therefore I get rid of that 2 factor. So we get this. I from 1 to 3, xi divided by ai squared, and then ui. Okay, so this is a normal field. Let v be any other field which is tangent to the surface, be a tangent field. Okay, on the ellipsoid. Then What is the covariant derivative? Well, this is just v of xi divided by the scalar ai squared times ui, and this is just I from 1 to 3 vi over ai squared and then ui. The reason is that since v of xi is just dxi at v, this is just vi. Okay. Now the dot product of z with uh, this expression. So I will use this result. So Gaussian curvature is given uh, by this equation. So I need to compute. So this is not plus, this is product. I'm sorry. Let's see if I have done something. Yeah, okay. What is this? This is just, okay, let me write this as a matrix. So this is x1. How would you take such a triple product? Cross product, and then here I have that product. I write z as the first row. So it is just x1 divided by a1 squared, x2 dot over uh, a2 squared, and x3 a3 squared. And then the second row is just this vector, so it is just v1 over ai a1 squared, v2 over a2 squared, v3 over a3 squared, and then the third one is w1 over a1 squared, w2 over a2 squared, and w3 over a3 squared. Okay, so what is this? If you compute this, you will get uh, 1 over, so here from the first row I can take a1 squared out, from the second row I took 1 over a2 squared out, and from the third column I take 1 over a3 out, and then the remaining terms are this, so I can write it like this: x times uh, v cross w. Here uh, uh, x is just the vector xi ui, v is the vector vi ui, and w is the vector wi ui. Okay, and if you compute this, moreover, this computation is just this is just by the choice, this is just z, x times z. So x is this, uh, z is this vector. I multiply with x, so this will be x1 squared, x2 squared, x3 squared, and then you add them all. So this will be just xi times xi over ai squared. So this is xi squared over ai squared, I from 1 to 3. And we know that since we are on the surface, this summation is equal to 1. So this is just 1. Hence, uh, the Gaussian curvature, which is just z dot product with sv cross sw divided by z dot Z. Uh, okay, so we have this. This is just 1 because this product is 1 divided by a1 squared, a2 squared, a3 squared times norm z to the power 4, where norm z to the power 4 is just, of course, this expression I from 1 to 3 xi squared ai squared, and then I have here norm is just square root of this, fourth power becomes square of this. Okay. So the Gaussian curvature is given by this at any point. All right. Here P of course has coordinates. Let's say P, suppose it is this point x2, x3, x3. So whenever you plug this, you plug these numbers here, you compute this, and then you compute the Gaussian curvature. Now we have a final remark. If this ellipsoid is a sphere, if a1 is equal to a2, a3, both all equal to r, in other words, the ellipsoid is a sphere of radius r, then of course this quantity becomes what? So this becomes 1 over r to the power 6 divided times this quantity, and this quantity is just, if you compute it, it is 1 over r to the power 4, because this is uh, r squared r to the power 4 divided by these are just, no, xi's will be 1, and these are just r, so you will get 1 over r to the power 4. So this is just 1 over r squared. Therefore, the Gaussian curvature is a constant function on a sphere of radius r, and its value is just at any point the Gaussian curvature is constant, which is equal to r squared. Well, uh, let me remark the following. The Gaussian curvature, if you think of this as a function, if you integrate this function on the sphere of radius r, so what would you get? This is the area form. This is just 1 over r squared times the area of the sphere. So it is 4 pi r squared. So you get 4 pi. In other words, what you get is independent of the shape of the size of the sphere. You always get 4 pi. This is not a coincidence. We will see that this is a particular case of the Gauss-Bonnet theorem. So this is a special instance of the Gauss-Bonnet theorem. We will see this at the end of the semester. We will try to sketch a proof of this theorem stated for more general surfaces, not just for the sphere, but for more general surfaces. Okay, maybe I have still some time. Let me talk about the Gauss-Bonnet theorem a little bit, and then next time I'll pass to a new section. So, uh, uh, description of Gauss-Bonnet theorem. This is a theorem about global properties of surfaces, actually. And how would you get a global property? You just add local invariants. And here is the theorem. Suppose I have a surface M, and suppose this is the surface of genus G. So this is a surface like this, and it has genus G. You may think of this as follows, actually. You have a sphere, and you attach this sphere and handles like this. Not N, but G handles. 1, 2, G handles. Since this is a smooth surface, I can talk about its Gaussian curvature. This will be a function on the surface, and the Gauss-Bonnet theorem is the following statement. If you take the Gaussian curvature, multiply with the area element, and integrate over the surface, what you get is the following. You get 4 pi times 1 minus g. Okay. This is a wonderful theorem. Why is that? Because here what you have is a geometric quantity, but you integrate over the whole surface, and it becomes a global invariant of the surface, and that invariant is actually independent of the local geometric properties. It's determined only by one invariant, which is the genus of the surface. Okay. To appreciate this, by the way, when g equals 0, you have just the surface, of course, a sphere. Therefore, this becomes, so the integral becomes 4 pi times 1 minus g, 1 minus 0. So you get 4 pi, something, we already obtained. Okay. Uh, okay. Why this is, something important or, interesting is the following. Uh, for example, take a sphere, a huge sphere like this. I know that the Gaussian curvature, when you integrate this Gaussian curvature on the sphere, you get 4 pi. And then here, add a tiny, add a tiny handle to this. A tiny handle. It can be as small as you want, okay? As small as you want. Once you put a handle like this surface becomes a torus now. So it's a genus 1 surface. So it is actually topologically equal to this one now. And so it is, okay, so this is this is a torus. This is a torus. uh, so it's a genus 1 surface. Therefore, if you add something like this, you see that Gaussian curvature doesn't change on this region and on this region. You just change it in a very small region here. But the suppose this is the new Gaussian curvature, and these two functions are the same on almost every point of the sphere except this small piece. But now this integral is what? This is just 4 pi 1 minus g, but g is just 1 since it's a torus, so it becomes 0. So even if you had add a small, very small handle to the sphere, uh, you change topology of the uh, surface, and therefore by the Gauss-Bonnet theorem, the total integral of the Gaussian curvature changes drastically. So here it becomes 0. Okay, so this is a very powerful result. All right, let's stop for today. I'll continue next time.